Alright, in this video we're going to continue our work on quadratic functions, and this time we're going to work with quadratic formula and a little bit on complex numbers. But we're going to start by solving this equation x squared plus 6x equals 1. And, much like last time, we're going to start by setting it to 0. So we're going to subtract 1 from both sides. And then we're going to try to factor, but we're going to see that we can't, because we can't think of two numbers that multiply to -1 and add to positive 6. So we're just going to know we need to add 9 to both sides. I recognize you might not just know you need to add 9 to both sides of this equation, and you really don't need to know that in this class. I'm just going to show you that if we were to add 9 to both sides of this equation, because we took the 6 and divided it in half and then squared it, we would have a perfect square trinomial right there. And so we could factor this into x plus 3 times x plus 3, which would be the same thing as x plus 3 squared. And then I would have the equation x plus 3 squared minus 1 equals 9. And this is something I could solve at directly. I could add the 1 to both sides to isolate the x plus 3 squared. I have x plus 3 squared equals 10. I could take the square root of both sides. That would bring in a plus or minus, so I'd say x plus 3 equals plus or minus the square root of 10. And then I could solve for x by subtracting 3 from both sides. What I just did there, that's like solving by completing the square. And while that may have been something you were required to be able to execute in Algebra 2, that's not something that we're going to really have to do in AP Pre-Cal. So I'm just going to show you that the once and show you that that technique, that's how we develop the quadratic formula that you probably learned about in Algebra 1. And in the rare event that we encounter a quadratic that's not going to be factorable, that's what we're going to do in this class. We're just going to use the quadratic formula. So what you see in your notes is kind of what I was saying, is that this technique would work for any quadratic equation. It would be a little more complicated if the leading coefficient wasn't 1, and I'm not going to really go into that in this video because that's not the point here. I'm not going to prove the quadratic formula for you in this video. If you're interested, I've got proof of it. In fact, I can probably make it come up there as like a clickable link, and you can go and see that if you're interested in seeing me complete the square on ax squared plus bx plus c equals 0. But we're going to get x equals -b plus or minus the square root of b squared minus 4ac all over 2a, just like we have in the past. Okay, so let's go back to the example we were talking about and make that happen a little bit faster. Alright, so if we were equipped with this formula and confronted with x squared plus 6x equals 1, we would set the thing equal to 0 because the quadratic formula only works when your quadratic is set to 0. We'd identify the value of a, that's the leading coefficient, is 1, b is the number of x's, c is the constant, and then we'd say, alright, x equals -b plus or minus the square root of b squared is 36. -4 times a times c would be +4 all over 2 times 1. And so we'd have x equals -6 over 2 is -3. Right? And if we're dividing this whole thing by 2, that means we're dividing each of these things by 2, plus or minus the square root of 40 over 2. Okay, and it's like, well, we're going to be able to show that the square root of 40 over 2 is the square root of 10. Let me get a different color real quick. So if I'm working with the square root of 40, that's the square root of 4 times the square root of 10. Okay? Because 40 is 4 times 10. So that's going to be the square root of 4 is 2, the square root of 10, I don't know, so I can leave that as 2 root 10. If I'm dividing that by 2, that's where I'm going to get, right here, -3 plus or minus 1 square root of 10, which is what I got by completing the square. Okay? And I'm of the opinion that you're just better off knowing the quadratic formula than trying to solve any quadratic by completing the square, because it's just it's more time consuming, and you probably have more experience using the quadratic formula anyway. So that's what we're going to do in this class. All right, now next we're going to look at the graph of y equals x squared minus 10x plus 21. Okay, and this is one that we're going to be able to factor, and that's for a good reason. I see where we're going with this. So the y-intercept, that happens where x equals 0. So y would equal 0 squared minus 10 times 0 plus 21. So that would be 21. And the x-intercepts, those are where y is equal to 0. And so that's 0 equaling x squared minus 10x plus 21. And that looks factorable. I can think of two numbers that multiply to 21 and add to negative 10. That would be negative 3 and negative 7. And we're trying to solve this equation, so we've got it factored. Okay, we're going to apply the zero product property and say that either x minus 3 has to equal 0 or x minus 7 has to equal 0. So that's going to give us our two x-intercepts. And equipped with two x-intercepts and a y-intercept, I think we should be able to sketch this parabola. So I know the graph of this thing's going to be a parabola, so I'll just get a little parabola going here. And it's got intercepts at 3 and 7. So just make that the x-axis. Now that's a very, very tilted x-axis. Let's try that again. Let's see. That's not... Okay, I thought I had it make an actual straight line. Let's get that better. That's a little better. So I can say that this x-intercept will be x equals 3, that x-intercept will be x equals 7, and then I can draw in a y-axis, which is probably not going to be drawn very much to scale, but it would be right there. All right, that's much better. Let the professional do it. And so I've got a pretty good sketch. We're going to say that this is y equals 21. That was the y-intercept, and that just kind of fits with what we knew. Okay, and I think that's really what we were going for here, was just get a sketch so that we could notice something about the vertex of this parabola. By the vertex, I mean this point right here, right at the very bottom. So when it asks for the coordinates of the vertex of the parabola, if you happen to remember the formula for the x-coordinate of the vertex from all the way back in Algebra 1 or Algebra 2, good for you. Okay, great. But if you don't, you can look at this sketch. Even this, this is not the best drawing of a parabola or the graph of y equals, x minus 3 times x minus 7 ever. But we can see that the x-coordinate of the vertex should be halfway between the zeros, just by the symmetry we know a parabola has. So I should be able to say x is equal to 3 plus 7 divided by 2. I should be able to average the x-coordinates and get the x-coordinates of the x-intercepts and get the x-coordinate of the vertex. So that would be 10 divided by 2, which is 5. And then y I could get by going back to the original statement of the equation. That's going to be x squared is 5 squared minus 10 times 5 plus 21. So that would be 25 minus 50 would be negative 25 plus 21. Feels like a negative 4 to me. And that's believable based on the sketch, right? It's down there below the x-axis where y would be negative. And so I'm saying that the coordinates of this vertex are going to be 5 and negative 4. Now we're going to solve the same equation using the quadratic formula, even though we know we can solve it by factoring. Okay, there's a message. So we're going to say, all right, x equals negative b. I'm actually going to copy in the quadratic formula, first of all, because, if we're trying to, commit something to memory and we don't quite have it yet, one of the best ways is going to be to write it down a bunch of times. The square root of b squared minus 4ac all over 2a. But also because this is kind of part of the message. So in our case, negative b would be positive 10 plus or minus the square root of b squared is 100 minus 4 times 1 times 21 would be 84 all over 2a. So that's going to be 10 over 2 plus or minus the square root of 16 is 4 over 2. And so this is, what we have is 5 plus or minus 2. Which means that the quadratic formula is really giving us more information than just the x-intercepts, right? It's telling us, the x-coordinate of the vertex plus or minus that distance from the x-intercepts to the vertex. Now, right there. Okay, so what we're seeing, 5 plus or minus 2, that's 3 and 7. So if we backtracked, what got us that 5? It was the 10 over 2, right? And that 10 over 2 came from the 10 here and the 2 there, which was the negative b and the 2a from the quadratic formula. So what we're going to say is that the x-coordinate of the vertex of any parabola, defined by y equals ax squared plus bx plus c, is going to be x equals negative b divided by 2a. And that's really why negative b over 2a is going to be the formula. All right, now maybe you can give this a shot on your own. So we've got two functions. They're both quadratic polynomials, and you're going to be asked to find the vertex of the parabola that corresponds to the quadratic function. One of them is given in standard form, the one on the left, and one on the right is given in factored form. Okay, my recommendation is use negative b over 2a if the function is in standard form, but use the cos of negative b over 2a, the fact that the vertex is halfway between the intercepts, on one that's factored, and just average the two x coordinates. So give this a shot on your own, see if you know what you're doing. I'm going to work these with video pause, and you can just check your work here in a couple seconds. All right, there you go. So on the left, I just used x equals negative b over 2a, which is going to be 8 over 2 times 2, and that left me with 2. And then I plugged 2 into f, and I got negative 2, and that gave me my vertex. That's probably the problem type you have a good amount of familiarity with from a different class in a different year. Okay, but on the right, if it's already factored, I can say that the x-intercepts on this graph are going to be x equals 5 and x equals negative 1, looking at the factors. And the x-coordinate of the vertex, I could average those x-intercepts, knowing that the vertex is halfway in between, and that would give me 2. Okay, and y is equal to g of 2, which is going to be 4 times 2 minus 5 times 2 plus 1, so replacing x with 2 wherever I see it in the formula for g. And I get 4 times negative 3 times 3, which is negative 36. So my vertex on the right is 2 and negative 36. Okay, that being said, there's nothing to say that you can't, on the right, distribute out 4 times x minus 5 times x plus 1 and then use x equals negative b over 2a. If that's what you feel more comfortable with, that's probably what you should do. Okay, but me personally, I'm going to see that coming if it's already factored. You can just kind of take a little shortcut and not do all of that multiplication, because that sounds like the type of place I might make an error. All right, now this next one is saying find the x-intercepts. And so with that one, we need to remember that means that's where y is equal to 0. And so we're going to have to decode that, and remember that means solve the equation y equals 0. Okay. But I think I'm going to let you try this one also on your own. Okay. Obviously, these are not going to be factorable, and you should probably just use the quadratic formula, because this is a video about using the quadratic formula. But you should work these with the video paused while I copy in the answers, and you can check your work here in just a couple seconds. Okay, there you go. So on the left, we've got x equals 1/4 plus or minus the square root of 17 over 4. That's what I got using the quadratic formula, and I am, being totally honest, assuming you have some degree of familiarity with using the quadratic formula. On the right, I'm just going to remind you something that you've probably also seen. Okay, we get down, we use the formula negative b plus or minus the square root of b squared minus 4ac all over 2a. We go to simplify, and 2 over 2, I know you know what that is. We've got the square root of 8, and we do need to simplify our radicals in this class, especially in a free response setting. Okay, we also need to be able to do it to recognize the correct answer in a multiple choice setting. So we're really going to need to be able to work with numbers like square root of 8. So if I'm over here and I say, square root of 8, okay, 8's got a factor of 4 in it, so that's 4 times 2. And I like 4 because it's a square number. It's something I can take the square root of. So 8, square root of 8 is 2 times the square root of 2. And so now I'm going to say 2 over 2, that's 1, plus or minus square root of 8 is, 2 root 2 over 2. Okay, so that's just going to be x equals 1 plus or minus the square root of 2. So I'm just reminding you, in this class, we're going to need to be able to take care of radicals and put them in simplified radical form. All right, now we're going to talk just a little bit about complex numbers. Now, as far as I can tell so far, it seems like in AP Pre-Cal, we don't really need to work with complex numbers all that much. We just need to recognize that they can be solutions to polynomial equations and kind of the nature of the way they come as solutions to polynomial equations. And that's something we'll talk about more a little bit later in the course. But we're going to just look at this quadratic equation, y equals x squared plus 9. Suppose we want to find where it's equal to 0. If we set it equal to 0, in the past, I think in algebra 1, you said, okay, x squared plus 9 equals 0, x squared equals negative 9. That can't happen. You take a number, you square it, how are you going to get negative? Okay, you take a negative number, you square it, you get positive. Take a positive number, you square it, you get positive. So we can't have x squared equals negative 9. Moreover, when we were drawing the graph of y equals x squared and doing, closely related graphs, you may have graphed y equals x squared plus 9. Looks like that. It's like regular y equals x squared, but shifted up 9. Something we'll talk about next time. The thing has no x-intercept, so it makes sense that the equation x squared plus 9 equals 0 would not have any solutions. But somewhere along the way, some mathematicians decided, what if we did? What if we did let the square root of negative 1 exist? What if we did have square roots of negative numbers and we just held them off as a separate class of numbers? What would happen? And it turns out all sorts of interesting stuff happens. Certain things that were difficult to show with real numbers were surprisingly easy to show with complex numbers. Complex analysis is a very interesting course. But this is kind of just the very start of it. Just suppose we were trying for x squared plus 9 equals 0. We tried to solve directly. Took the square root of both sides, so of course we would need plus minus. And then we had the square root of negative 9. It's we know the square root of 9 is 3. And we have that property where we can split off, radicals over their factors. And so if we had the square root of negative 1 and we just called it some imaginary number, maybe good stuff would happen. And that's kind of the level we're working at here, is that we just need to know that the square root of negative 1 is I. So I guess at this point, the main piece of information that you need to know would be, definition of I is that I equals the square root of negative 1. Okay. There's all sorts of nice arithmetic problems and other problems we could do with this that we actually did in my Algebra 2 class last year, but we won't be doing in this AP Pre-Cal class, and simply because it's not going to be tested on the AP exam. Maybe in a later math course you'll be able to do interesting stuff with complex numbers, but we'll just lightly touch on them here. Now, if you're following along in the notes book, you'll see that there's 4 equations here that we need to solve, and we'll go in and solve all 4 of them. But I'm going to start with this one because kind of, it's something different for you. So just like all the rest of them, we need to start by setting it to 0. So that would be x squared plus 2x plus 5 equals 0. And we try to factor and not have any success, so we're going to need to use the quadratic formula. And we'd see x equaling negative b plus or minus the square root of b squared minus 4 times 1 times 5, b minus 20, all divided by 2a. And we'd see x equaling negative 2 over 2 is negative 1 plus or minus the square root of negative 16 divided by 2. Okay. And we can take the square root of 16. So that means we're going to be able to take the square root of negative 16 also. Okay, if the square root of 16 is 4, then the square root of negative 16 we're going to call 4i. So we'll go in there and replace that with 4i. And then, well, the 4 is still a real number, so we can divide 4 by 2. And so this would be negative 1 plus or minus 2i. Okay, and so that's how we're going to obtain complex solutions using the quadratic formula. Okay, we're not going to ever be able to factor and get complex solutions. That's not going to be part of this course. We're just going to use quadratic formula because it's easy enough to use. I had something else to say. Oh, yes, of course. This -1 plus or minus 2i. Where we're going with this in AP Precal, and I think really the farthest we go here, is that if you're going to have one solution to a polynomial equation that's a complex number, you're actually going to have a second one, and they're going to be closely related friends, like we're seeing here, the -1 plus or minus 2i. But I'll leave the specifics of that for, about a month or a month and a half from now. Now I think you should try this out on your own. We're at about the 20-minute mark, so I think it's really time for you to get to practicing. So try all three of these. I'm going to just bring in the solution, so you should try these with the video paused, and then check your answers against the work I'm about to show. All right, there it is. So see, the same principle still applies that applied earlier, that if we were only seeing one power of x at a time, like, in this equation, we only had 3x squared plus 75 equals 0, and over here we're squaring x plus 1, and we don't have any just number of regular x's, we were able to solve that directly. Just isolate x, take each side to appropriate power, and, continue on our way. Whereas down below, where we had more than one power of x at the same time, we had to set equal to 0, try to factor, and then default back to the quadratic formula, and that didn't work. But those are good examples of ways that we can obtain complex solutions to quadratic equations. All right, so in conclusion, here we use the quadratic formula to solve quadratic equations that were not factorable, and also to help us find the vertex on the graph of a parabola. We saw that some quadratic equations have complex solutions, and the graphs of those parabolas had no x-intercepts. So, at this point, you really just need to continue practicing solving your equations, working with these things, and getting a little bit stronger one day at a time. So thanks for being here, thanks for watching, hope this helped.